Okay, so this is to follow up our continuous probability distributions unit. We're following up the normal distribution. So we spent some time learning about how to figure out the probability of ranges of specific values, less than a certain amount or greater than a certain amount or in between certain amounts from a distribution of data with a mean and a standard deviation, as long as that distribution followed a bell curve shape, or what's called a normal distribution. So this is sort of a continuation of that, but the continuation for this one is a little bit different. What it really follows along with is the idea that because this normal distribution is so commonly seen all over the place, we remember that we have continuous variables, which is what the normal distribution is designed for. It's a continuous probability distribution that's described by a function, okay, by a line or a curve. We look for the area under the curve, knowing that the full area is 100% or 1, frequency of 1 or a probability of 1 for the whole area under the curve. And then we use proportions of that area designed by the equation to help us figure out ranges of values and so on. But for this application, we can also apply it for discrete variables. What if, instead of talking about the number of the mass of Smarties in a package, instead we were talking about the number of Smarties in a package? Well, if they're normally distributed, most of them will probably be a specific amount, let's say 40 or something like that. And then of course there could be 39 or 38 or 41 or 42, and so follow along this same pathway. So what we've done is we're adapting a continuous probability distribution for the use with discrete variables. Okay, and of course that adaptation is a really important one. Now to start off with, what I really do is I have an addendum to your notes. So I have this part of your note, and I've got the next page where we have examples. But before that, I have sort of a compare and contrast. Okay, and in this compare and contrast that we have here, what you see is sort of two ideas, two situations. Okay, so the normal distribution, this is what we've done already. This is for continuous variables. Okay, so example is the mass of a bag of chips, okay, produced on an assembly line, okay, at the sort of serving size, a bag of chips, not a huge one. So let's say the mean mass is 40 grams and the standard deviation is 2.5 grams. Okay, so when we were going to figure out, for example, the mass of acceptable bags of chips that aren't too light, that aren't too heavy, but that you can actually sell to the consumer, let's say here we want to find out the probability between 37 and 43 grams. Okay, what's the probability, or what frequency, what amount of chips fall within that category? And we can use the normal distribution to do that. So what do? Again, we draw our normal curve. We draw our barriers at 37 and 43, realizing that our mean is at 40. Now I've set it up nice and beautiful with nice round numbers. It doesn't have to be these round numbers, it doesn't have to work out perfectly. I just made it so it's easy for you to do a comparison between what we've seen already and what we haven't seen yet, but what we're doing today. So what do? Again, we take the barriers, okay, and to find an in-betweens, remember we take the big barrier minus the small barrier, because remember that when we use our z-scores and we use our normal distribution table for our z-scores, it's the value from here and downwards. So if we were to get from 43 and use the z-score for 43 like we've calculated here, that z-score for 43 would be from 43 all the way down and including this extra tail here, all this area in here. Okay, we don't want that tail, so we want to cut off that tail from 37 downwards, and so that's why we do the big minus the small. Remember, we have to take probabilities that are greater thans or less thans, and we have to adjust them so that they're all less thans. So the probability that between 37 and 43, again, we write down 37, write down 43, we find out the barriers, we do a z-score, and then we realize that probability of being between 37 and 43, okay, is the big barrier, probability that x is less than the big barrier, minus the probability that x is less than the small barrier. So I take this whole area, that's the probability that x is less than 43, and then I take this whole area and I cut off that area, so I subtract from the probability 37 and downwards, okay? And so we're left with an in-betweens, and in-betweens is the big minus the small, okay? So now that I've got that strategy set up, I've got how I can actually get there. From there, I go, okay, well, I do my difference. Then I say, okay, how do I find that the probability x is less than 43? Well, if it's a normal distribution, it follows a normal curve. But for us to turn our data into the normal curve, we need to make it from a mean of 40 to a mean of 0, and a standard deviation of 2.5 grams to a standard deviation of 1. And the way to do that is by doing a z-score. So that's called normalizing your data. It's taking the data that you have and making it fit the normal curve that we know oh so well. So that's what we do. We do a z-score for 43 and we get positive 1.20. We calculated it up here. We do a z-score for 37. We get a negative 1.20. We calculated that up here. And then what do? Well, we find out the probability of a z-score. We look it up on our trusty z-score table. Remember the z-score table? Here it is. I'm not going to show you how to look it up because you probably would have done it a million times by now with all the homework I gave you. And we get for positive 1.20, z-score of positive 1.20, we get 0.8849. And for a negative 1.20, we get a 0.1151. We, of course, subtract those values. We never subtract z-scores. We never do any arithmetic with z-scores. Z-scores just get us probabilities. We do the arithmetic with the probabilities and the probabilities only. And we do that difference and we get about 77%. Okay, that means 77% of the bags of chips in this distribution, okay, are between 37 and 43 grams, or the probability of grabbing any particular bag and having it be between 37 and 43 is about 77%. That's what we've done already. Well, what we're doing today is we're bringing in a discrete variable. So instead of 40 grams for a massive bag of chips, it's going to be the number of Smarties in a box. I'm still going to make it 40. I'm still going to make the standard deviation 2.5. Still the same data. I'm still going to look from 37 to 43. But what I'm going to do is I'm going to make an adjustment so that I can do it for discrete variables. And the adjustment that we have to make is, if you remember, discrete probability distributions, a discrete value of 37 actually occupies a space. A discrete space. The same way that 38 does, and 39 does, and 40 does, and 41, and 42, and 43. They occupy bars, but they do ascribe this same normal distribution pattern. And as a result of that, we can say to ourselves, we can try and use this approximation in order to figure it out. Let's use this calculation to do this, but we have to make it a little bit of an adjustment. We have to correct it. Because what happens is 37 actually doesn't start right at 37. 37 stretches halfway between 37 and 38. Okay, and so halfway between 37 and 38 is 37.5. So that means that this bar has a thickness to it. This 37 didn't have a thickness to it because it was a massive bag of chips and it was a continuous variable. This was infinitely small and thin. But this one has a thickness to it. And so it goes from 37.5 to 36.5. Okay, similarly for our 43, the same thing happens. 43 goes from 43.5 to 42.5. So it's got a thickness to it. So if we're dealing with a discrete variable, we have to make an adjustment. That adjustment is called a continuous correction. So we can't use a 37 for our barrier and for our z-score. What we have to do is actually say to ourselves, all right, if I want between 37 and 43, I want to include the 37 and the 43 because it's less than or equal to or greater than or equal to, then what happens is I need to include the whole 37 bar and the whole 43 bar. If I include those whole bars, then what I need to do is I need to include the left-hand side of that range. So rather than stopping at 37, I slide a little bit over and I go to 36.5. Same idea for the 43. Rather than stopping at the 43, okay, that bar has a thickness that reaches as far as 43.5. So because I'm including the bar in my distribution, I've already shaded it all in this example, instead of using a 43, I use a 43.5. So what happens is this. When I have discrete data, between 37 and 42 is not between 37 and 42. What happens is 37 turns into 36.5 and 43 turns into 43.5. Now sometimes it's one side of the bar and sometimes it's the other side of the bar, depending on whether or not you include it. So you have to think about whether you're including that bar in your distribution. Here, 43 is included, so we include it in the distribution and shade it all the way to the edge. Here, 37 is included, so we include it in the distribution, we shade it all the way to the edge. If it was greater than 37 and less than 43, then we would include them and we would use the upper range. Okay, so it'd be 42.5 and this would be 37.5. But in this case, it's a greater than or equal to, which means it's 37 or more and 43 or less. So we include 36.5 into 43.5 to encompass those bars. This from here to here is called a continuous correction. Okay, it's a continuous distribution that we're going to use. We have to correct it for discrete variables, and so we do a little correction. It's called a continuous correction right here. Okay, now everything else after I do this, exactly the same. So it may seem like we're blowing your mind. It's exactly the same thing as it was before, except of course we have to do the continuous correction. Okay, and it's either going to be 0.5 above or 0.5 below, whatever delineation it has between the most acceptable, nearest acceptable value below and above. That's what the halfway between the two of them is going to be, and that's where the bar is going to lie. Okay. So what do I do? Well, I've got an in-betweens. So how do I do an in-betweens? Well, remember, it's always going to be a big, the probability of x being less than the big, minus the probability of x being less than the small. Okay, so still done the same way here. From here to here, same way as from here to here. Exactly the same way. Okay, it's an in-between, so I go big minus small. Okay, do my z-scores, same way. For 43.5, I do a z-score. For 36.5, I do a z-score. Okay, same calculation that I would have done here. Same z-score calculation, except instead of using 37, I use 36.5. And instead of using 43, I use 43.5. Okay, and so I get a z-score a little bit higher of 1.40 and a little bit lower of negative 1.40. I get then the probability of this. So this is again still normalizing the data, going from my data to the normal curve. We've got our z-scores. When we go from our z-scores, we go to our probabilities, z-scores to our probabilities, and then we finally do the subtraction. We don't subtract z-scores, we subtract probability values. Okay, and so here we get a probability of 0.8384, which is significantly different from 0.7698, but of course we're encompassing a whole value from half one way and half the other way. So as a result, it actually ends up being a fair bit more. So the probability of finding between 37 and 43 Smarties in a box is 83, almost 84%, or 84% of the boxes are going to have between 37 and 43 little candies in there. Okay, so that's the idea that we're going for. So when we go to do these examples, this is what we have to do. Okay, so have a look over that, look at the comparing and the contrast, and see the difference between the two. This is what you know, this is what's new. So read that over. It's the second page of your scanned notes, I think. Either way, again, sorry about that. We've got, again, a standard deviation of 1 and a mean of 0. Still the normal curve. Still the normal curve. But we're modeling for a discrete variable here. Okay? So here's an example. I'm going to do another one with a box of Smarties. Obviously, I'm not very creative. A box of Smarties has a mean of 48 Smarties. That's 48 candies. Discrete. You have 48, you have 47, you have 50. Nothing in between. A standard deviation of 4.3. So my mu is going to be 48. My sigma is going to be 4.3. Okay? Any box with more than 55 pieces will result in unacceptable extra cost. We're not quite sure what that's going to mean yet. Okay? A quality control will reject any box with fewer than 44 pieces. Okay? So they're adding a little bit of an application to here. In other words, we can't keep or sell different sizes or different amounts of Smarties in a box. So, what percentage of boxes chosen will contain too few? So what does too few mean? Okay, we've got our mean, we've got our standard deviation. It's following a normal distribution. Okay, so keeping that idea in mind, well, too few, well, quality control will reject any box with fewer than 44. So I want to find the probability or percentage, that's a relative frequency, of x being too few, so it's going to be less than for sure. The barrier is 44. The big question is it less than 44 or is it less than or equal to 44? Okay, fewer than 44. So that means it has to be less than 44. 43 and below, not good. That's too few. So I'm going to leave that as less than 44. Now the first thing that we're going to do is we're going to realize Smarties are discrete. If they're discrete, then you have to do a continuous correction. If it's discrete, you have to do a continuous correction. Have to. Because this is a normal distribution, it's for continuous variables. So what do? I turn this into, or I go equals, and I go ahead and I adjust it. Now, it's still going to be a less than. I can make that a less than or equal to, but I want to visualize this. So what I'm going to do, here's my candies in a box. What are they, 48? 48 is the mean. So we're over here at 44. Now notice how I'm drawing a bar here. That's number one, because it's discrete, I draw a bar. And now I draw a bar at 44, but I employ two barriers to it. Now I want a less than, which means I know I'm going to be coloring in this part of the curve, less than, right? But I want less than 44. Less than 44 means I don't include 44. I want below 44. So I stop at the edge of this barrier. Okay, that's less than 44. I don't include the bar because 44 is still okay. It says fewer than 44. That's not okay. So what is this barrier right here? Well, because they're separated, the next one is going to be 45 and 46 and 47. Then that means, and the next one down here is going to be from 44 is going to be 43 and so on. This is going to be 43.5. That's halfway between 43 and 44. So when we do the continuous correction, we're not going to use 44 because that's the center of the bar. We're going to use the edge of the bar that's appropriate in this case. And because we're not including the 44, we're going to use less than 43.5. And that right there is my continuous correction. That's what that is. I'll put a little CC for continuous correction. And that's all. That's the only difference between this and anything we've been doing. It's a less than, which is easy, right? So probability that x is less than 43.5 is equal to the probability, and then we just got to do a z-score. Same as usual. Z-score 43.5 minus my mean, 48, all over my standard deviation, 4.3. Okay? And that's, of course, going to be, excuse my mathematical form, about a negative 1.05. Okay, if I do that calculation correctly. All right? And if it's a negative 1.05, that means if I want the probability of x being less than a value, I don't have to do anything fancy with it. It's already a less than, so I go straight to the z-score. That's normalizing my data, changing it from 43.5 to the normal curve, which is a negative 1.05. I looked that up in my trusty z-score table, which is right here. Negative 1.05. Which is right here, 0.125. Wait a minute, negative 1.05. Oh, sorry, down by 1. I'm getting old here. Negative 0.1469. So that's 0.1469. That's right here in the table, 1469. There we go. Okay. All right. And so then that means, of course, there's some sort of closing statement. Therefore, prob or percent of boxes less than 44, too few, is 0.1469 or about, well, rounded 15%-ish. Okay, or 14.7%. Okay, that means 50% of the boxes are too small or have too few Smarties in them. We're cheating the customers out of Smarties. Okay, or of course that the probability of grabbing any particular box and having too few is going to be about 14 to 15%. Okay, so let's look for another one. What percentage of boxes lie within an acceptable range? Well, what's the acceptable range? Okay, well, I'm going to go ahead and draw my normal curve here. My little sketch. My 48 goes here. We already know too few is 44. Right? And we draw the two barriers for that bar. Okay? Now, any box with more than 55 pieces, make that 55, and that'll have two barriers for it. Okay? So if we have more than 55, not acceptable. Okay? We want to lie within an acceptable range. So we want the probability that x is going to be between 44 and 55. Okay, in this case, it's going to have to be less than, or, oh, it can't be equal to, wait. More than 55, so less than or equal to. And it's got to be greater than or equal to 44, because it's okay to have 44. Fewer than 44 is not okay. So that means that this and this is what we don't want. Those are the unacceptable boxes. We want the ones that are acceptable, okay? Now, if they're acceptable, it means they're going to include this bar, which means they're going to occupy this, let me get my hatchings through here, this space here, okay? And it's going to go from this edge right here to this edge right here. This edge is not 44, it's 43.5, and this edge is 55.5. So my continuous correction says really it should be between 43.5 and 55.5. Okay? And then from there, of course, and it's an in-betweens, Okay, so I'm going to go through it the normal way. So that's my continuous correction. Go through it the normal way. So that means this is going to be the big barrier minus the small barrier. So I'll turn them both into less than or equal to. So those I can do for my z-score table. Beautiful. Okay, and then what I want to do, of course, is to take my data and turn it into the normal distribution table. So that means I have to normalize my data, which means I need to do a z-score for 43 and a z-score for 55.5. So z is going to be 43.5 minus 48 all over 4.3. Or if you remember from up here, we already did it at 1.05. We can cheat. That's all right. Z is equal to 55.5 minus 48 all over 4.3. It's going to be a little bit more. First of all, it's going to be positive, okay? And second of all, it's going to be, let me just cheat on my solutions. Or you can, of course, be following the notes as we go along, so you'll already have this as well if you want to. And those are the two z-scores. Okay, so the big has got a z-score of positive 1.74. You don't always have to put the plus in there, but it's sometimes good to have it in there. Okay, and then certainly for the negatives, definitely make sure you put the negatives in there. Okay, and then you look them up in your trusty z-score table. You look them out in your z-score table: 1.74, 1.74, 0.9591, and z-score of negative 1.05. Oh wait, we already had that one. Negative 1.05. Oh yeah, it was 0.1469. 0.1469. Subtract those two values. I'm going to do a quick little cheat with my answers. 8122. That means, therefore, the number of acceptable, or I should say percentage of acceptable boxes is 81.22%. Or, again, the probability of randomly sampling a box and getting one that's acceptable is about 81%. Probably not very good as a company, but I'm just making up this stuff, so who knows. Okay, so that's how to do less than and in betweens. The only thing that's different is these bars. That's the thing that's different. However, there is a calculation that's a bit unique to discrete variables, and it's different from continuous variables because we're actually asking for a specific value. Okay, look at this one. What's the probability that a box selected at random contains exactly 50 pieces? Well, we couldn't do this. Well, I guess we could sub it into the equation, but it would be so small. But we couldn't do it for a continuous variable. If this was 50 grams, we couldn't do this. But because it's 50 candies, it's discrete, we can do this. Okay, so when we go to do this, because the bar actually has thickness to it, it actually is its own little range. So here's 48, right? Here's my 50. Boop, boop, boop. I'm going to make it really fat here so I can see what I need to see. But I actually want to know the probability of 50, which is this area in between these two bars here. And that goes from what to what? It goes from 49.5 to 50.5. So it's actually a range between these two values. So the probability that x is equal to a specific value that's discrete using a normal distribution is actually a range and in-betweens. So this probability of x is equal to 50 is really the probability that x is going to be, that x is going to be between 49.5 and 50.5. Half above, half below. It's going to be less than or equal to, yes, it's going to be greater than or equal to that particular value. It doesn't really matter because that's our continuous correction. So when x is equal to 50, which we couldn't do for continuous, for discrete we can do, and it's going to be that range there. Again, to do an in-betweens, it's always less than the big minus the probability x is less than the small. Okay, and then what we do from there, we have our data. We need to turn it into a z-score, or we need to normalize our data to turn it into the normal curve. So we have to do z-scores. 49.5 minus 48 all over 4.3. Really ugly, but you've got a nice, beautiful solution for yourselves. So make sure you follow along with that one. Oops. I'm trying to use my cheat sheet over here. Positive 0.35, and then for 50.5, minus 48 all over 4.3 is actually a positive 0.51. Okay, both are above, of course, and one's a little bit more above than the other. So it doesn't seem like it's that much of a difference. Positive 0.51 for the big for 50.5, and for 49.5, 0.35. I go ahead and I do my probability for that, 0.6950. Of course, I looked that up in my probability table, but I'm trying to keep this video from being under an hour. And then for 0.35 would be 0.6368. Do a difference there, and we get 0.0582, or about 6%. So therefore, prob of a 50 candy box is 0.0582%, or about 6% of the boxes have 50 in them. Okay. Last question, just a simple application question. If I make 15,000 boxes, how many are expected to be acceptable? Well, the percent acceptable, if you remember from our previous example, these were the acceptable boxes, 81.22%. And if you assume they're randomly sampled and properly distributed amongst all the different employees who are packing the boxes, or all the different machines who are packing the boxes, or all the different days, or whatever, 15,000 boxes, you would just take 0.8122, multiply that by 15,000, and you would get 12,183 boxes, approximately, are acceptable. Meaning, of course, you got about 2,900 or 2,800 boxes that aren't acceptable. That is what it is. Okay, homework is here. It's not a lot, okay, but it does take a long time to get used to it. And pay close attention while you're doing those. 2 and 8 are really good examples to do with those. So have fun.